All right, so we're going to look at some properties of definite integrals. I want to talk about those a little bit, but before we even get to that, just to keep the process fresh in our minds, let's do one more example. Use of a definite integral from -1 to 2 of 3x squared plus 2 dx. And we can check our answer using the graphing calculator. So we'll show you how to do that as well. Okay? So first of all, we want to use the limit definition. So question here, do we need to use intervals that are not equal, or can we just use the b minus a over n? Okay? Yeah, we can. This is just a 3x squared. There's nothing too fancy going on here. If I use the even intervals, I'm going to be able to get it down into either i's or I squares or I cubes maybe, all right, when I do my sums, all right? So we will go ahead and use the constant delta x of b minus a over n, because remember our limit definition is the limit as n approaches infinity of the sum from I equals 1 to n of f of c sub I times delta x. Okay? Now, what are a and b in this case?
B is 2 and A is -1.
Good. It's the integral from -1 to 2. So the interval we're talking about is from -1 to 2. So 2 minus a -1 over n is 3 over n. Okay? So I have that part. Now we need c sub I. What is c sub I?
A plus delta xi.
A plus delta x times I. Very good. Okay, so a, we already said, was -1. So it's -1 plus delta x is 3 over n, so it's 3i over n. And then another thing you might want to do before we start plugging stuff into the actual formula is go ahead and do f of c sub I. Well, f of x is 3x squared plus 2. So we have to do 3c sub I squared plus 2. And like we just saw, c sub I is 1 plus 3i over n. Okay, you'll notice I'm doing a lot of this work over on the side, and I'm going to wait to plug it into the formula. That'll help me kind of keep things a little cleaner, a little neater, but also it helps me not have to write as much. I don't have to copy the limit of the sum on every step here. Okay, so at this point I just FOIL 3 times 1 minus 6i over n plus 9i squared over n squared plus 2. I distribute the 3 and combine like terms, and that gives me a 5 minus 18i over n plus 27i squared over n squared. And now I have everything that I need to put in to my limit definition. Okay? Are there any questions? Okay. Now, as I'm putting this in, remember we have the option of, we could either distribute the delta x into f of c sub I, or we could pull it out in front of the sum. Which would you guys rather do?
Distribute.
You want to distribute? Okay, let's distribute. Alright, so we have the limit as n approaches infinity of the sum from I equals 1 to n, and I'm going to distribute the 3 over n to the f of c sub I. So it's now 15 over n minus 18 times 3 is 54i over n squared plus 3 over n times 27i squared over n squared is an 81 I squared over n to the third. Okay? So notice there, I distributed my delta x into f of c sub I. Okay? And you'll notice, like we anticipated, all we have are I and I squared and a constant that is inside of our sum. So we were right in just using a constant width for the intervals. Okay? So at this point, I've got to simplify some. I'm going to take the limit as n approaches infinity. Let's do the sums now. What's the sum of the 15 over n?
15.
Yeah, it's 15. It's 15 over n times n. Because it's a constant. Alright? Then I have minus the constant 54 over n squared times the sum of the i's. What's the formula for sum of the i's?
N times n plus 1 times 2n plus 1 over 6.
That's the squares.
That's square one.
This one is just n times n plus 1 over 2. Okay?
Oh, that's for alright.
The last one,
Yes, for that.
it's going to be plus 81, and that's going to be over something n cubed. And here's the formula for the I squares. N times n plus 1 times 2n plus 1 all over 6. Okay? So at this point, we just need to simplify enough so that we can take the limit. Okay? So, limit as n approaches infinity of 15 minus 54n squared plus 54n. That doesn't matter because we have the 54n squared over 2n squared. What's the limit as n approaches infinity? 54 over 2, or 27. Okay, so 15 minus 27 plus, now we got to do the last part. We have an 162 n cubed plus 3 times 81 is 243 n squared plus an 81n all over 6n cubed. So what's the limit as n approaches infinity?
162 over 6.
Yeah, 162 over 6, which actually comes down to 27.
That's 15.
Okay? So 162 divided by 6 is 27. And so it's, the whole thing here equals 15. Yes?
How do you know when you can and can't use the b minus a over n?
Basically, look at the function that you're integrating. Here it's just a regular old polynomial. So you're going to be able to do that one. It's a quadratic. If you had something like the square root or something more complicated, you'd have to mess around with that with that delta x.
And is that where you would get like an extra piece of information to help you figure it out?
Yeah, a lot of the times you are given that. Although, if you remember, it's just basically think about how could you make it work out. There's a little bit of trial and error in there. Like if it's a square root, you got to make it so that you end up with I squared or I cubed. So the easiest thing would be to make your delta x be like the I squared over n squared, so that when you square root it, you just have i's.
Okay.
But then you'd multiply it by the b minus a still.
Okay.
That's where the interval comes in. But the rest of it, you could just kind of make it work. If it were if it were a x to the fourth, we don't know how to do that. So you might make it square root of I over square root of n, so that when you raise it to the fourth, it ends up being an I squared.
Okay.
And then you have something that you can work with. Okay? Alright, so there's our example. Let's take a look at some properties of definite integrals. Okay? Here are 5 properties. I want to illustrate a couple of these. So the first one here, the integral from a to a. The integral from a to a. So let me illustrate this here. Here's a. If I'm going from a to a, I'm finding the area of that line segment right there. What's the area of a line segment? 0. Okay? A line segment has no area. That was one of the properties you learned back in geometry. Points take up no area, lines take up no area. They have a length but no area. Okay? So, and by the way, those of you who either have or are taking statistics, if you remember dealing with continuous distributions, you couldn't take the probability of exactly one value because the probability was 0. So you might have used normal CDF on your calculator. But guess what normal CDF on the calculator is doing? It's integrating. It's integrating from your interval like a to b, and it's finding the area under that curve.
We talked about Raymond's sum today.
Oh, you did? Okay. So yeah, so it's all tied together here. Probability and statistics with calculus. Yeah, and the normal PDF is how did you actually graph any of the bell curves? Okay, so when you hit normal CDF on the calculator, it's graphing the bell curve and then it's doing an integral of that bell curve. But if you have an interval that has no width, then you have no area. Okay? Then we have something that we looked at actually last week briefly, but we list it here again. If our function is integrable from a to b, a to c, and c to b, then you can split it up into separate intervals and add them together. So for example, if I wanted to integrate from a to b, I could, if I wanted, pick another number c in here, and I could find the integral from a to c, and then add to it the integral from c to b, and that'll give me the same thing as the integral from a to b. Okay? Alright, I'm going to skip the last one on this column, and I'm going to do the next one on the second column there, and then I'm going to come back and handle these last two. Alright, this one right here is kind of interesting. It says the integral from a to b of f of x dx is the negative of the integral from b to a of f of x dx. And what does that basically tell us?
It's the same back and forth.
Well, it's not the same back and forth.
It's the same value, but it's negative.
Okay, if you go from right to left to get your area, as opposed to going from left to right, you're going to get the same value but opposite signs. Okay, so in other words here, direction matters. Just like a positive velocity and a negative velocity indicated direction. Okay.
Because the sign of the dx is related to the direction, so that's why we can get negative value from
Okay. Yeah, and basically what's happening here is, you know, you could have the same area, but if I'm going this way, I'm going to get a positive area. If I'm going this way, I'm going to get a negative area. Okay? So it does matter which way I'm going. Okay? Now you might say, well, how do we get negative areas? Well, remember that while integration is based off of the area under a curve, that area doesn't have to represent physical area. That area under the curve could represent, say, the profit for a company. Okay? And in that case, yeah, you could end up negative. You could end up losing money. Alright, so we can't have integrals that equal negative values. Okay? And we'll talk about that a little bit more here in just a minute. These last two, I wanted to point out something. You'll notice here it says the integral from a to b of f of x plus g of x dx is the integral from a to b of f of x dx plus the integral from a to b of g of x dx. In other words, if I have the integral of a sum, I can take the integral of each part and sum the integrals. Okay? We also have this one here, the integral from a to b of k f of x dx. So we have a constant multiple. We can pull the constant outside the integral, find the integral, then multiply at the end. That's really helpful in keeping our numbers small. Or if you had like a radical 3 in there and you don't want to mess with radicals the whole time, pull it out, do the integral without it, and then multiply by radical 3 at the end. Or a pi, or anything like that. Okay? But the reason why I wanted to point this out specifically is because here, remember, where did we get the integral from? What's going on mathematically? Okay, it is an antiderivative, but think up above what we just did.
The area?
It's a limit of a sum, okay? Now, if you look at these properties here applied to limits and to sums. So it makes sense that they would apply to integrals as well. When you had the sum of two functions, you could take the sum of one plus the sum of the other. When you were doing the limit of two functions added together, you could do the limit of one plus the limit of the other. So these are just carryovers. These just carry over from limits and sums. Now notice it would have to work for both of them. It can't just work for one or the other. It would have to work for both. Okay? Alright, so let's do a couple of examples using these. And you ought to like these because these aren't going to be too terribly difficult. We're not actually going to evaluate here, but here's one, example 2, that you'll run into. Set up a definite integral that yields the area of the region. Now what region are they talking about? This one's a little bit ambiguous. So I clarify here, we're talking about total area that's enclosed by the function, the zeros, and the x-axis. Okay? So you'll notice I actually graphed it over here on the right. And so we're talking about the 0, here's a 0, here's a 0. Okay? And we have this function here. So you notice actually, because this crosses the x-axis, we kind of have actually two different regions. And one thing you might have noticed is that every area that we found so far has always been above the x-axis. And that is because if you're taking the integral to find area of a region that's below the x-axis, you actually are going to get a negative area. Okay? So when I do this down here, that's actually going to give me a negative number. And depending on the problem, that could be okay. All right? Now, in this case, it asked for total area enclosed. Okay? I don't want the net area, the positive minus the negative area. I want the total area. So I need to make that positive. In other words, if I'm taking the integral here, you'll notice this goes from -2, this is 3, and this is 5. Okay? I'm getting the integral from -2 to 5 of the absolute value of this. Now, the reason why it's absolute value is because I want total area. I want to make whatever is negative positive. All right? So the way we can deal with this is actually by combining that second property by splitting this into two separate intervals. And also I can deal with the top one, the fourth property, where we can deal with the negative area. Okay? So the way I could write this is the integral from -2 to 3 of the function as it is, x cubed minus 6x squared minus x plus 30 dx. And then somehow I need to make the other area positive. Okay? So I could simply do this, minus the integral from 3 to 5. Okay, so when I do the integral from 3 to 5, I'll get a negative number, so if I subtract the negative, it'll make it positive. Or if I wanted to, I could do plus and put the absolute value outside here. I don't care how you do it, as long as you make that second area positive somehow. Okay? So that's one way that you could write that to calculate the total area, even though this is a negative area. You can make it positive, so you're actually finding this area up here. Okay, the positive area.
Are you adding those two, like, are you getting like a net area, or are you subtracting that little piece from like the bigger piece?
No, if I did just the integral from -2 to 5 and didn't use the absolute value at all, that's what that would do. It would take the area that's above it and subtract the area below.
Okay.
Okay, I don't want to do it for this particular problem. Okay?
And you would need the graph, or you could just find the zeros, right? Well, you would need to know.
We would find the zeros somehow, however you wanted to find the zeros. Yes?
Is there any way to use your calculator, like once you have to find the integral of that, or?
Yeah. Yeah. We could actually do it. How are we doing on time? The last couple examples are really short, so we can just do this. Yeah. See you.
So like on that last task, like if we had just known how to do that, that would have saved us like a lot of work.
Well, no, because I asked you to show work, so. Yeah, here, let's go ahead and put a video in here. Turn that around. Okay. Can you guys see? All right. Okay, so we're recording. in the recording here. Got our inception moment. All right, so what I'm gonna do actually is I'm gonna clear this stuff here. And I'm gonna punch in my function. So x cubed minus 6x squared minus x plus 30. Now notice I don't even have to bother graphing it. I'm just going to go out to the home screen and do the integral. So if you go to math, down here at number 9 is function interval, and it gives me a nice little template. So I'm going to do the integral from -2 to 3. So -2 I'm putting in as my lower bound, 3 I'm doing as the upper bound. I want to do that for y1, so I'm going to go find y vars function, punch in y1, and I'm going to integrate with respect to x. So I put the dx there. Okay? That makes sense? So now I hit enter, and the integral of that is 93.75. So that's 93.75 minus, now I do the integral, so I'm going to hit second entry so I don't have to type all that again. But I just need to change my bounds. So change that from 3 to 5. Hit enter. Notice it gave me a -8. So I'm subtracting here a -8. And this whole thing, the total area then is going to be 101.75. Notice if I had just done the integral from -2 to 5, it would have been 93 minus the 8, 85.75. So that's what you were talking about before, Rebecca. It would have actually given me a net area rather than a total area. Okay? All right, so that's how you can do it with the calculator. You can check yourself. Obviously, we're going to expect to see all your work. Okay? So, no shortcuts here. Oops. Get back on the pencil. Okay. So now, just using the properties here, let's say I wanted to find the integral from 0 to 6 of f of x dx. I'm given the integral from 0 to 3 of f of x dx equals 4, and the integral from 3 to 6 of f of x dx is -1. So what am I going to do? Yeah, just add them together. Because to find the integral from 0 to 6, I can take the integral from 0 to 3 and add to it the integral from 3 to 6. So I have 4 plus a -1, which is 3. Okay? That's pretty easy. Sure beats doing limits, right?
So the answer is 3 instead of 5.
The answer is 3. Notice here I'm not doing absolute value because it just said the integral from 0 to 6. It didn't say find a total area or anything like that. It just said integrate from 0 to 6. Okay? How about this next one here? The integral from 3 to 6 of -5 f of x dx.
5.
It's going to be 5 because I can pull the -5 out and then do the integral from 3 to 6 of f of x dx. So that's -5 times a -1, which is just 5. Okay? So, this stuff is a little bit simpler to work with, but I will tell you with this, as we're getting into all these rules, I had given you a list of antiderivatives before. Obviously, we're going to need to know those. All right? You're going to have a lot to memorize as we do these. You're not having to do sums and limits anymore, but you will have to memorize the rules.
This is the last lesson in like on our code test.
No, no. On Fusion Day, we're going to be looking at the fundamental theorem of calculus, which is actually how we're going to evaluate this, okay? You know how to take the antiderivative of the cubic. You know, it's x to the fourth over 4 minus 6x cubed over 3 minus x squared over 2 plus 30x plus c. Fundamental theorem of calculus will help us use the 3 and the negative 2 to actually get that value of 93.75. So that's what we'll be doing on the Fusion Day. Okay?
Cool.
All right, that's it.